Okay, I'm going to look at some solutions to this assignment. So we're graphing rational functions. So the function given here is f at x is, let's just fix this autofocus. There you go. F at x is equal to negative 0.5 x squared plus x plus 1.5. Okay, so easiest thing to do when your leading coefficient is a decimal is factor that out from the entire term. It just makes it much easier to deal with. So we have negative 0.5, and now we have x squared minus 2x minus 3. Okay, way easier to deal with because factored, that just turns into negative 0.5, x minus 3, x plus 1. Okay, so that's for the original function. And we're going to look at its reciprocal as well, which is 1 over f at x, which is simply going to be 1 over all that same stuff. And so all the features of these two graphs are related to each other. Starting with the x-intercepts are very obvious for this one. Right, the x-intercepts are going to be x equals 3 and x equals negative 1. Now, if we take a careful look at the reciprocal, we can see that there are no values of x that are going to make the numerator equal to 0. So for the reciprocal function, there are no x-intercepts. None. For its y-intercepts, the y-intercepts are going to be, well, if we go back to the original function, you can see it's right there. Right, they're always going to be at f equals 0, f at 0, that is. So that's going to be, that turns into 0, that one turns into 0, leaving us with just 1.5. The y-intercept for this guy is going to be 1 over 1.5. The nice thing about dealing with reciprocal functions is that once you know a y value, 1 over that y value is the equivalent point for the same x on the other graph. So this is technically 3 over 2. So this is going to be 1 over 3 over 2, which is 2 over 3. Okay, the y-intercept is 2/3. Asymptotes. So I'm assuming this means vertical asymptotes because there are no other ones involved here. If for this one, but there are none. For this one, we've got a vertical asymptote at the zeros of the other, right? So the zeros of this one are the asymptotes of that. So the vertical asymptotes are going to be at x equals 3 and x equals negative 1. The horizontal asymptote is going to be through y equals 0. And we know this simply because the numerator of this function is of a lower degree than the denominator, automatic 0. Okay. So max or min? In this case, I'm actually going to leave this until after the function. So, well, you know what? No, let's do it. Because the vertex of this function, remember this function looks like this, right? And this function, because it has 2 roots in the denominator, is going to look something like this. So let's say those are 2 asymptotes. It's either going to be something like that. It could potentially cross in this middle portion, or it could be the upside down version, the same thing. And again, this could potentially cross through here. That could happen. That would only happen if there were zeros that existed in this function. We know already that there are none, so we are pretty confident that that's not going to happen. It's going to be underneath, and this guy would be something like that. So we don't know which one's which. What we're looking for is this. And the nice thing is that the minimum, the x-coordinate of the minimum on the original graph is going to be the same x-coordinate of the maximum on this other graph, or the equivalent point anyway. So in this case, because this has got a negative leading reciprocal, this is actually a maximum situation. It's upside down. This is a maximum, meaning when we flip the whole thing over in the reciprocal function, it's going to be this version. It's going to be that guy there. So the vertex, or the max or min, in this case it's max, and the max is going to be at the midpoint between the x-intercepts, so 3 plus negative 1 over 2, which is 1. That's the x of the maximum, say x max, and we're going to say y max, is going to be just whatever the value of the function is at 1, which is going to be negative 0.5 plus 1 plus 1.5, so that's 2. So the max point on this one is 1, 2. For this one, we can find the midpoint between the vertical asymptotes, which is the same as what this is going to be to find the x of the minimum. And in this case, we've got, it's going to be x equals 1. And then we plug that value back into the original function to find out what the y value is. So the y of the minimum is, or what the actual minimum value is going to be 1 over negative 0.5 times, well, 1 minus 3 is negative 2 times 1 plus 1, which is positive 2. So that's negative 4 halved, but negative, so positive 2. So this is going to be y equals 1/2. So the minimum point for this one is going to be 1/1/2. Okay, there's that one. Now, where's a positive or negative? This is way easier to deal with if we just graph it first. So let's do the graph, shall we? So let's just slide this over and put this guy in, just like that. And I'm going to mark at positive 3. So this is 1, 2, 3, 1, 2, 3. That's not a mark, that's a mistake. And this is going to be negative 1. So negative 1, positive 3. Those are our vertical asymptotes. I'm going to plot any other information I have, right? Our x-intercepts, none. Our y-intercept is going to be at 2/3. So if this is 1, it's at 2/3, it's roughly there. And our vertex point, sorry, I forgot to do my horizontal asymptote, can't really tell it's there. Our minimum point is going to be at 1/1/2. So this will be here at 1, but just a little lower than that guy, so a half. And we can actually see from this being at 2/3 and this being a half that we are actually, like, it is in fact going to be it is going to be a reflection of this guy here. Right? So this is going to do something like this. And it goes back up like that. Okay, which is nice. Now, what happens on these sides? Well, we got to do a little bit more work to figure that stuff out, right? So for our original function, our max is at 1, 2, so it's up here, and it just comes down like that. I'm just going to do it really light because I don't want to clutter our graph a little bit too much. Okay, so now I'm going to set up an interval chart just so I can see where things are positive versus negative. And that is the easiest way of answering that question of where's the positive intervals, where's the negative intervals. So I'm going to set up, for first of all, for this guy, we can tell just by looking at the graph, right? There it is. And from the features we know about polynomial functions, that the positive intervals, will be between the asymptotes. So from negative 1, inclusive to positive 3, right? Positive intervals. The negative intervals is going to be outside those limits, so it's going to be between negative infinity and negative 1. Both do not include the ends. Actually, it doesn't matter in this graph. That's fine. Union with positive 3 and positive infinity, right? So from here to the left and here to the right, this function is negative, the original function, the one that's light. For this guy, a little bit different. Again, interval charts are the best way of figuring this out. So we'll do that. And our key points on our interval chart are going to be -1 and positive 3. So we'll put that in there. -1 on that borderline, positive 3 on that borderline, right? So we've got x is less than -1, between -1 and positive 3, and x is larger than positive 3. Down this column, we are going to list all the factors. So in this case, all the factors that matter. So there's a positive 1, which doesn't matter. We have a -1/2. I'm just leaving an extra row here. I'll fill that in a second. I do have to include the constant term. I've got x -3 and I've got x + 1. Okay, and this is the overall 1 over f at x function. And what I'm going to put in this extra row that I've left there is the test point. So the test point for this interval is anything less than -1, so I'll use -2. For this one, anything between -1 and 3, so I'll use 0 because it's easy. And for this interval, anything bigger than 3, so let's do 4, right? Try and keep our numbers simple. No matter what the value of x is, this -1/2 is just going to be negative all the way through. Now, -2 minus 3 is negative. -2 plus 1 is negative. 3 negatives make positive. That does not seem correct. It's not. It's because it's negative. That makes more sense. I had an alarm bell go off there because usually these guys switch, right? It's going to be negative, positive, negative. The fact that it was positive, and I'm looking at the graphs showing the second interval being positive already, made me go, something's wrong. Okay, now I can confirm my suspicions. Now 0 goes in here to make this negative. 0 goes in here to make that positive. So that overall is positive. And now 4 goes in here to make this positive, and in here to make this positive. So overall, this will be negative. So our intervals of being positive is going to be this one here. Our interval for being negative are going to be these two there. Okay, so intervals of increase or decrease are a little bit trickier because we do have to put them in the graph first to take a look at them. Another way of doing this algebraically is test a really big negative number like -10,000 and then check another number in that same interval closer to the asymptote and see if it is further down on the graph or further up on the graph than that first one at -10,000. So you test like -1,000 or -10,000 and then test -10, right? So it'd be much closer. So we'd see a distinct like sloping of upwards, or we'd see a distinct sloping downwards, right? But we already know it's negative, so we know it's here, somewhere in this region. So it's a matter of, is it doing some weird thing like that, or is it doing something like that? And we know it's the second one just because we're used to these shapes. Okay, so that's one way of doing it. The other way of doing it is just use our interval chart to be like, okay, well, I know in this region here, it's below the x-axis, and so it has to skirt the edges of both asymptotes, right? The horizontal one and the vertical one. This one's already positive, and this last one is negative as well, so it's going to do something like that with our arrows at the end. I apologize for my left arm here. It's really ugly. Right, and that's what that is. Okay, so intervals of increase are anywhere where the left side is going to be less than the right side if we test values. So I can actually see that this is higher up than over here, right? It's sloping downwards. So this interval here is an interval of decrease from here to that vertex point that we found. So that would be at 1. We have another interval of decrease from there to the asymptote. So from 1 to -3 is going to be increasing. And then because this from the left to the right is going upwards, see, from this point to that point, it's going up, this is an interval of increase. So summarizing, decrease is going to be between -infinity and -1. It's going to also be between -1 and +1. Intervals of increase are going to be from +1 to +3 and from +3 to +infinity. Note that the things that include these asymptotes are not inclusive boundaries. So they're the roundy brackets, like these guys over here. These ones that are cut off over there. Those are the roundy brackets. The square brackets include that endpoint. Okay, so that's everything for the first question. It's just quite a lot in there, I agree. There's a lot to process. And I didn't write out the intervals. Oh, I guess I've the positive intervals and negative intervals and the increase and decrease intervals I did not bother to write, but I did describe them. So feel free to rewind and watch them again. Okay, let's take a look at the next question. So the next question is sketch the function by finding the holes or asymptotes, x, y intercepts, and n behaviors where applicable. Okay, so we have here the function f at x is equal to 2x squared minus 7x plus 3 over x plus 1 times 2x squared minus 9x plus 4. Okay, so factor everything first, always, no matter what. All right, so I'm looking for two numbers that multiply to make 6, and they add to make -7, so that'll be -6, -1. So that numerator portion goes from being 2x squared minus 7x plus 3 to 2x squared minus 6x minus x plus 3, and then factor from the first two to x to get x minus 3, and then factor the negative out of the second two to get x minus 3, to get x minus 3 times 2x minus 1 is the factored form. Okay, cool. Now let's do that bottom one. And that bottom one is going to be 2x squared minus 9x plus 4. I'm looking for two numbers that multiply to make 8 and add to make negative 9. These are nice and easy, so minus 1 minus 8. And that will work. So I've got 2x squared minus 8x minus x plus 4. Factor out the 2 from the first two terms to get 2x x minus 4, and factor the negative out of the second two to get x minus 4. So I get x minus 4 times 2x minus 1. Fantastic. Okay, so let's rewrite our factored form of our rational function. And I have in the numerator 2x minus 1 times x minus 3. And in the denominator, I have that x plus 1 that was not considered in our factoring process, because why would we? And the other two factors, which are 2x minus 1 times x minus 4. Okay, there we go. So now, excuse me, we can see that the 2x minus 1s cancel out, which tells us there's a hole at x equals positive 1/2. What's left in the denominator are our asymptotes. So VAs at x equals negative 1 and x equals positive 4. In terms of horizontal asymptotes, the degree of the denominator is 1 more than that of the numerator, meaning that there is no horizontal asymptote other than the 1 through 0. HA through y equals 0. Okay, we've got the holes in the asymptotes. Fantastic. We need to know the x and y intercepts. So the x-intercepts are going to be anything that makes the numerator 0, right? Now we consider this graph in this form now, in its simplified form. We just have to remember that when we get to the hole, we consider like that point does not exist. In fact, we should find the y-coordinate that goes with that. So let's do that as well. So the y for this is going to be equal to 1/2 minus 3 over 1/2 plus 1 times 1/2 minus 4, which is going to be minus, what is that? 6 over 2 minus 5 over 2 divided by whatever the product of, this is 3 over 2 times minus 3.5 is minus 7 over 2, which is minus 5 over 2, and this is going to be 21 over 4, so it'll be multiplied by 4 over 21, and that's a negative. So negative times negative is positive. Great. That's 20 in the numerator, 42 in the denominator, which is 10 over 21. Great. So that is the y-coordinate of our hole. So we can plot the hole 1/2, 10 over 21. Right away, just plop that point on there, and that also tells us a point that this graph will pass through. Okay, so our x-intercept for this one is anything that makes the numerator 0, and we can very clearly see that that is going to be at x equals 3. Our y-intercept will happen when x is equal to 0, so y will be equal to, well, negative 3 over 1 times minus 4, which is positive 3/4. So there is our y-intercept. There's our x-intercept. We have our asymptotes. So let's look at end behaviors now. And so end behaviors, we can anticipate them going to be approaching our horizontal asymptote. But the best way of testing it is to put a very large value in our function. So we can test for our end behaviors. We're going to put in f at 10,000, which will be 10,000 minus 3 over 10,000 plus 1 times 10,000 minus 4. I'm just going to get out the old trusty calculator here, also known as my phone, which you can't use on tests ever. And I'm going to punch in these numbers. So I've got 9,997 divided by, I'm put in brackets the denominator, 10,001 times 9,996. Close that bracket. And we get, boom, a tiny number very close to 0, but it's positive. So 0.0001. Testing f at negative 10,000. We would get negative 10,000 minus 3 over negative 10,000 plus 1 times negative 10,000 minus 4. Okay, that's the calculation I'm doing. So I've got 10,003, that's negative, divided by, put that in brackets, the product of that, which is going to be negative 9,999 times the product of that one, which is negative 10,004. 10,004. Close that bracket, and that gives us negative 0.001. So to describe this, we can say as x approaches infinity, because that's getting close, right? I mean, it's not close to infinity, obviously, but if we put in larger and larger numbers, we're just going to get smaller and smaller decimals. The point is that it was positive, so that matters too, right? And so the only thing left for us to do is to test a point, because these essentially function as our test points for the intervals to the left of our left-hand asymptote and to the right of our right-hand asymptote. The only thing we haven't tested is what happens in between. So let's just make sure that we know where the graph is going to hang out. And we can also test really close to those numbers on the top or the bottom. So we can say near asymptotes. We can say as x approaches, let's say the left-hand one, negative 1, from the negative side. So we pick a number just smaller than negative 1, so negative 0.001. And we'll see if we get a very large positive or very large negative number, because that'll tell us if it's going up or if it's going down, right? So we are going to use negative 1.01, okay? So 1.01, that's negative, minus 3 is going to be, that's our numerator, divided by the entire denominator in brackets. So it's going to be 1.01, the negative version, plus 1 times, oh, you know what, I made a mistake. So sorry. Let's try that again. 1.01, the negative one, minus 3, that's our numerator, divided by, open a bracket, open a second bracket, and that's going to be for 1.01, negative version, plus 1, that's this section here, times, open a bracket, 1.01, the negative version, minus 4, that's the second bracket. So that is our entire denominator, and that entire thing is going to be equal to negative 80. So it looks as though y is approaching negative infinity. So going down, that's what that means. And as x approaches negative 1 from the positive side, we pick a number just bigger than it. So let's use 0.99. Right, so I'm going to say 0.99 minus 3. That's our numerator, divided by our denominator, which will be 0.99 negative plus 1. That's our first bracket, times our second bracket, 0.99 negative minus 4. Close that. That gives us 40. Y is approaching positive infinity. And then we do it one more time with the other asymptote. So as x approaches positive 3 from the negative side, so we'll use something just smaller than that, like 2.99. So I'll say 2.99 minus 3, that's our numerator, divided by our denominator, which is 2.99 plus 1, that's our first bracket, times our second bracket, 2.99 minus 4, and that's our denominator. That entire thing is going to be 0.02. That's not right. Let's try that one more time. So 2.99 minus 3 is that, divided by, open brackets, 2.99 plus 1 times 2.99 minus 4. 0.002. So that does seem to be going upwards. Y is approaching infinity. And then from the other side, as x approaches 3 from the positive side, we can use 3.01. Let's do that. 3.01 minus 3. That's our numerator divided by our denominator, which is 3.01 plus 1 times 3.01 minus 4, that's our denominator. That's our entire product, so it's negative. Y is approaching negative infinity. This feels like it should be approaching the asymptote. I guess a good way of checking if this is actually approaching infinity, if this is just starting its journey down to infinity, or if it's actually coming up towards the horizontal asymptote, would be to plug in another number even closer to the asymptote. Like, so we just did 3.01, so you can do 3.001 or 3.0000001. And instead of 2.99, we can use 2.9999999 and see what comes out. Okay, not going to bother. So now we have all this information. Yeah, we're good to go. We're good to go. And so these guys here yield as x approaches infinity, y approaches 0 from the top. And this guy here tells us as x approaches negative infinity, y approaches 0 from the bottom. Okay, so we have a lot of info. Let's put it all together. So here's our graph. And let's mark our asymptotes first. So -1 is our asymptote. So x equals -1, and then +3, right? +4. That's why I was getting weird results, because I was approaching the wrong number. So that should have been 4. That should have been 4. So let's see if that still holds true. I'm not going to recalculate it, but I'm pretty sure those numbers are. No wonder they're being so weird. Yeah. Okay, so let's just try these again. So we're going to use 3.99, right? Minus 3 is that, divided by, in our denominator, 3.99 plus 1 times 3.99 minus 4, -19. So this is 3.99, so it's this one, so this is negative infinity. Cool. And then this one we test 4.01. 4.01 minus 3, that's our numerator, divided by 4.01 plus 1 times 4.01 minus 4, which equals a positive number, so that's positive infinity. So I did have them backwards because I was testing two values that were both essentially to the left of that second asymptote. So that was why that was being weird. Thought something was wrong there. 1, 2, 3. This is 4. Okay, so this is x is equal to 4. X equals 4. And our horizontal asymptote is through 0. Y equals 0. And then let's do our end behaviors first, because we have them all listed out here. So as x approaches infinity, y equals 0 from above. So it goes like that. And as we approach 4 from the positive side, we're approaching infinity. So it's going up like that. So we can pretty clearly see this is going to connect just like this, something like that. And then let's do the other end behavior as x approaches negative infinity, y equals negative infinity. So it's -0. Sorry, 0 from underneath. There it goes. That was the word I was looking for. And as x approaches 4 from the, negative 1 from the negative side, we're going downwards, which fits, right? If it was doing this and then crossed up there, that'd be weird. We don't like that when it gets weird. We usually only have things crossing asymptotes when they are, what's the word I'm looking for here? When they're using oblique asymptotes. So this is already strange. I'm not sure why it's doing this. This is being bizarre. But let's take a look at our other end behaviors, because when we approach negative 1 from the positive side, we go up to infinity. So that's actually accurate. These guys should be doing the opposite thing, because if they're doing the same thing, that'd be a bit strange. And then as we approach 4 from the negative side, we approach negative infinity. So it's doing something like a cubic function in the middle, doing one of those little jiggy jog things. And so yeah, now let's put in all our intercepts. So and that'll give us a more accurate depiction of what's happening in our graph here, right? And so our x-intercept is at 3, which is right here, there at that point. And we have a hole. Let's use the hole to help us graph, shall we? Oh, let's use the y-intercept at 3/4. So there's 1. So this will be 3/4. So this is going to go scoot down through there and scoot along there and go back down again. And then, but we will have a hole at x is 1/2, and this is just a hair under a half, the y coordinate. So it's like half, like here, which kind of fits again with the shape that we were thinking of, right? So this is going to go down like this and take a right-hand turn and cross there, and then go all the way down and rejoin its friend here. And that's it. And so I'm just going to quickly throw this function into Desmos. Oh, I forgot to make this a hole. So this should have been a hole. That guy there, that's an open circle. This is why we don't use pen. Let's go into the Desmos app. And we'll just plug this equation in and see how accurate I was. I really hope that I got this, because if I didn't, it's kind of embarrassing. So 2x squared minus 7x plus 3, and that's the numerator. And then the denominator is going to be x plus 1 times 2x squared minus 9x plus 4. There it is. I mean, that looks very, very similar. And another interesting thing to do is we can actually, I don't know if you can do this on the mobile version, but if I scroll this along and I get to 1/2, you can actually see there, right there, there's the hole. Hard to get it, but we nailed that one. Really killed it. Okay, so the second question and the final equation. The final question is match the function by finding the holes or asymptotes. Sketch the function. Sorry, this is a little blurry. Sketch the function by finding the holes or asymptotes. So it's the same kind of question, but this one is using our favorite f at x is equal to x squared plus 3x plus 3 all over x plus 1. And we can see that the degree of the numerator is 1 more than that of the denominator. That already tells us that this is going to have an oblique asymptote. This is the one case where I'm going to be like, I was going to say don't factor it yet, but we will have to factor it. So let's see if we can factor this. We cannot. Fun. So you can't factor the numerator anyway. If you could and something canceled out, that'd be strange. But now what we're actually going to do is we're going to say, well, there's a vertical asymptote. We can tell right off the bat at x equals -1. Just because this isn't factorable doesn't mean it doesn't have roots. So we do need to know if or when it crosses the x-axis. So I'm going to quickly test the determinant just to see if it has any roots, because it could have no roots, and in which case I'm saving myself some trouble. And I'm just going to check b squared minus 4ac. So a is 1, b is 3, c is also 3, and b squared minus 4ac is going to be 9 minus 12, which is -3. And so a negative b squared minus 4ac means no roots. So x-intercepts, none. Y-intercepts, however, will be what happens when we plug in x equals 0, or we just look at the ratio of the constant terms. So 3 over 1, right? Because this will be 0 plus 3 over 0 plus 1, which is 3 over 1, which is just 3. Y equals 3. There we go. Okay, so now we have to find our oblique asymptote. Because there are no holes, we have our vertical asymptote. It's right there. Cool. But we still need to see what's going on with that horizontal asymptote. But because that degree is larger than that degree, that means it is an oblique asymptote. So I'm going to do this using long division. You're welcome to do synthetic division. It really doesn't matter. But we're just going to look at the parts and see what they mean. So if I have x plus 1 dividing into x squared plus 3x plus 3, right? So x goes in x squared, x times, and multiply that through to get x squared plus 1x, and subtract, we get 2x, bring down the 3 to get 2x plus 3. X goes into 2x, positive 2 times, multiply it through to get 2x plus 2 to get 1. And so our f at x becomes x plus 2 plus 1 over x plus 1. Right, that's how we write that statement. It becomes this quotient plus the remainder over the original divisor. Okay, so what this tells us is this is the equation of the oblique asymptote. We have an oblique asymptote at y is equal to x plus 2. Okay, cool. That's fine. And so for our end behaviors, we can plug in a really large value for x if we want. Thing is, this is just going to add 2 to it. It's not really telling us anything. When we put in a really large value of x for this actually tells us if we're above or below the asymptote. So we are going to approach the vertical asymptote from the left and the right, and I'm going to plug in as x approaches infinity by testing a really large value, but I am not going to bother with this part because I know it's just going to be a large positive number adding a little bit to it. And when I do a negative, it's going to be a really large negative number adding a negative fraction to it as well. So what we're going to see is this little piece here will actually tell us if we're above or below the oblique asymptote. Let's graph what we have so far, and then I will come back to these final end behavior tests. So I have minus 1. It's my 1 asymptote. X equals minus 1. And then I'm going to plug in my oblique, so it's at positive 1, but I'm just doing an approximation here. This is not quite. This should be like kind of like that. And so this is my oblique asymptote. And where does my oblique actually touch the x-axis? So 0 equals, it's going to be at minus 2, so it's actually going to cross over here. It's going to do something like this. There it is. There it is. I had a bit of trouble with that one. Again, don't work in pen. Sorry for that. Okay. Yep. Okay. We're good. We're good. So now I'm going to test values because I don't know where anything goes. What I do know is that my y-intercept's at y equals 3. So over here this is 1, 2, 3. So this is going to be right here is the only point on the whole thing that we actually have. So we're going to need a little bit more detail. Now, my intuition tells me after looking at this is that we're going to have something that goes through here, and then that means we're going to have the opposite on the other side. I also know that we do not cross this x-axis here because we have no x-intercepts. Okay, so there's no point in drawing anything to go above that point. So I'm still going to test everything and do all my end behavior tests. So I'm going to say as x approaches -1 from the left, and I have to test as x approaches -1 from the right, as x approaches positive infinity, and as x approaches negative infinity, right? Those are all the tests I have to do. So to test these, I just pick test values and plug them on in, right? Okay, cool. So I'm going to plug in for, as we approach this one, I'm going to plug in -1.01. Okay, I'm going to plug that into the original equation and see what I get. Okay, so I'm going to take, I'll just plug that in, negative 1.01. For this one, I'm going to use negative 0.99. 99. Cool. So I've got 1.01, the negative version, squared, plus 3 times 1.01, the negative guy, plus 3. There's our numerator, divided by, in brackets, 1.01 negative plus 1. There's our denominator, and the end result is a negative number. So we're going to say y approaches negative infinity. Okay, so that is represented by this arrow here, which is kind of what I was saying before intuitively, right? That's what we're hoping to see, right? Always good to get an intuitive sense of what it should look like before you start actually testing numbers, because if something doesn't match what you thought, it's not always right to assume that you were wrong, if that statement makes any sense. Now I'll test negative 1.99 to see what happens when we approach from this side. My intuition tells me it's going to be going up based on where the y-intercept is and how these functions generally behave. So let's test it. I have 0.99, the negative version, squared plus 3 times 0.99 negative plus 3. There's our numerator, divided by 0.99 negative plus 1, which equals 101. Okay, so y is going to approach positive infinity. I'm just going by whether it's positive or negative. It's really what I'm looking at here. And again, if I want to further test it, I could pick a number even closer to the asymptote, like negative 9.9999999. Just add more zeros, it gets closer, right? Or add more nines here and it gets closer. Add more zeros between these two numbers and that gets closer. And so you'll see your numbers getting bigger and bigger in the positive or negative direction, as the case may be. For testing as x approaches positive infinity, I am just going to test this portion because I could easily plug in. Okay, so like let's say I pick a big value of x, like 10,000. I can add 2 to that. I'm perfectly capable of that. So I know it's going to be 10,002. What I don't know is where this line that is the oblique asymptote, what's it going to be at that point? Well, it's going to be at 10,002 plus something positive means it will be up a little, plus something negative means it will be down a little. Right? And it'll be the same thing on the other end. I'm going to get a negative 10,000 is where this line, at negative 10,000, this will be at negative 9,998, plus a positive number means it would be just above it, plus a negative number means it'll be just below it. And that'll tell me my end behavior. Okay, so I'll plug in 10,000 just to this portion because that's all that's relevant. And so I have 1 divided by 10,000 plus 1. You probably already know what this result is going to be. Boop. It is very tiny but positive number, right? So I didn't draw in that arrow. There's that arrow, and then there's my other arrow, and then I connect them, making sure I pass through my y-intercept, which is very poorly drawn. 1, 2, 3, yeah, whatever. Okay, so it's going to do something like that. That's not my best graph, to be honest. And then let's do our final end behavior as x approaches negative infinity. So this was y approaches, how do we write this? X plus 2 from above. So we'd say plus. Right? Because it even says on the sheet, use plus or minus to indicate from above or below or from left and right. So this is from above. And for this other one, I'll plug in negative 10,000 into this little extension portion. I say 1 divided by 10,000 negative plus 1, close to brackets. It's negative, no surprise. Okay, so it's not a shocker. So this will approach the asymptote from below. And so my graph will be over here like that. And then I just connect these guys together. Don't cross the x-axis. Everything else is fairly arbitrary. And there it is. Yeah, we did pretty well, I think. Okay, so there is the solutions to that assignment. I hope you found where your errors were and have corrected them forever in your brain. Have a great night and a great day.